In this video, we'll be looking at the ferrite number prediction of stainless steel welds. In previous sections, we had discussed the advantages of ferrite presence in austenitic or duplex stainless steel welds. The volume fraction and morphology of ferrite in these stainless steel welds is determined primarily by the chemical composition. For this reason, it is possible then to empirically predict the weld microstructure based on the alloy composition. In this presentation, we will be discussing the historical development and application of the prediction diagrams. The first major advancement in predicting the microstructure of stainless steel welds was an empirical diagram published by Scheffler in 1949. Figure 36 shows the typical Scheffler diagram, which is used to predict the microstructure of stainless steel welds on the basis of the amount of austenite and ferrite forming elements in the steel. In the y-axis, you have the nickel equivalent from 0 to 33, which is calculated using the formula in the brackets. The formula includes nickel, carbon, and manganese, which are strong austenite formers and stabilizers. The x-axis consists of the chromium equivalent from 0 to 38. The chromium equivalent formula in the brackets include strong ferrite formers assigned different coefficients. The diagram itself is divided into different regions based on the transformation behavior of the steel during cooling. In the light blue section, the liquid solidifies as primary austenite and remains fully austenitic as it cools. In the same section, where you have lower chromium equivalent values, you have the austenite transforming to martensite. In the red section, the liquid solidifies as primary delta ferrite. As the nickel equivalent decreases, the amount of retained ferrite increases. The next major advance in prediction diagrams was proposed by Long and DeLong in 1973. The Long and DeLong diagram displayed refines the region of the Scheffler diagram by enlarging the scale and adding more precise line positions to enable a more accurate prediction of the ferrite content, especially in the 300 series austenitic stainless steel welds. In addition to changing the scale of the diagram and improving the accuracy of the predictions, the DeLong diagram also incorporates two significant changes. Firstly, the incorporation of nitrogen on the nickel equivalent formula with a coefficient of 30. Secondly, they introduced the term ferrite number to define the ferrite content of the weld by its magnetic response. If I can make an example on how I can use this diagram to predict a weld microstructure. Given a chemical composition of the weld, I can use the formulas in the figure to calculate the nickel equivalent and chromium equivalent. Let's say the chromium equivalent works out to be 22 and the nickel equivalent is 14. This will mean that the ferrite number will be 12 and the ferrite content in the microstructure will be approximately 10.7. This is indicated by the red dot in the DeLong diagram shown. The use of ferrite numbers, which are highlighted in red, rather than the ferrite percentages which are highlighted in blue, was prompted by the inherent inaccuracy involved in measuring the ferrite contents of the weld using optical methods like point counting. Because of the difficulty in correlating the magnetic force to the ferrite percentage, an arbitrary scale, the ferrite number, was selected. The most recent prediction diagram was published by Kotecki and Sievert in 1992. The Welding Research Council WRC 1992 prediction diagram overcomes many of the problems associated with the Scheffler and the DeLong diagrams. The authors completely removed the manganese and added copper in the nickel equivalent equation. This eliminates the systematic overestimation of the ferrite number. As discussed previously, Studies have shown that the solidification mode in austenitic stainless steel is more accurate than the ferrite content for predicting the resistance to hot cracking. Kotecki and Sievert included the solidification mode boundaries in their diagram, which are highlighted in the red broken lines. These lines enable the user to predict the primary solidification mode of the austenitic welds. The A and AF phase fields in the diagram denotes primary austenitic solidification. Alloys situated in the F and the FA phase fields solidify as primary delta ferrite and will be resistant to hot cracking. For some chromium equivalent and nickel equivalent values beyond the lower limits of the ferrite number lines on the WRC diagram, martensite may be present in the weld metal. Figure 39 shows the WRC diagram with superimposed martensite phase boundary. Below the thick dark line on the diagram, samples showed a magnetic response related to the presence of martensite. Above the line, no martensite was detected in the welds. Kotecki and Sievert also showed that the axis of the diagram can be extended to predict ferrite numbers for dissimilar metal joints. Figure 40 shows the WRC diagram with extended scale for dilution calculations. Application of this diagram for predicting weld microstructures for dissimilar metals is illustrated in the following example. In example 1, you have a AISI 1050 medium carbon steel in which a weld layer is deposited using the 312 austenitic stainless steel electrode. The chemical composition of the base metal and the electrode are shown in the table. We are asked to use the diagram to predict the weld metal microstructure. Using the chemical composition, the calculated chromium equivalent and nickel equivalent of the base metal is 0 and 17.5 respectively. And for the 312 electrode, the chromium equivalent is 29 and the nickel equivalent is 11.9. In shielded metal arc welding, the typical dilution of the weld by the base metal is 30%. If the chromium equivalent and the nickel equivalent for each composition is plotted in the diagram and a line is drawn between the 2 points, point A corresponds to the 1050 steel and point B corresponds to the 312 electrode. A weld pass of the 312 with 30% dilution from the AISI 1050 steel lies at point C, located 30% of the distance from point B to point A. Mathematically, this can be calculated to get the chromium equivalent of 20.3 and nickel equivalent of 13.6. The diagram predicts at point C an austenitic weld microstructure with 5% delta ferrite.